Hi, this is the Renegade Mathematician here. Thanks for joining me again. And today we're going to continue our discussion of cofactors and minors and also cover an important example. But we're going to start off first by noting that the last time we proved the cofactor expansion theorem, which states that a determinant can be decomposed into the sum of the products of entries in any row or column you choose and their corresponding minors. Anyway, in other words, a determinant D is equal to a sub 1k, a sub 1, capital A sub 1k plus a sub 2k times capital A sub 2k, so on and so forth, blah, blah, blah. In that case, we'd be expanding about a column, but it works for rows too. But today, let's start with a definition. Okay, an upper triangular matrix is a square matrix whose entry in the ith row and jth column is 0 when I is greater than j. Okay, a lower triangular matrix is a matrix whose entry in the ith row and jth column is 0 when j is bigger than I. Okay, so in one case, I is bigger than j, the rows are bigger than the columns. In the other case, the columns are bigger than the rows. Okay, a matrix that is either upper triangular or lower triangular is called triangular. So if it's one or the other, we can just call it triangular. So here's what an upper triangular looks like, and there's what a lower triangular looks like. Notice that the upper triangular matrix has zeros below the diagonal going from the first entry to the last entry, and the lower triangular matrix has zeros above the diagonal going from the first entry to the last entry. Okay? And if we define the main diagonal of the matrix to consist of all entries of the matrix for which I is equal to j, then we can say that an upper triangular matrix has zeros below the main diagonal, and the lower triangular matrix has zeros above the main diagonal. So that's why we call it triangular, because it forms a triangle. Anyhow, moving on. Here's an example. Okay, if A is a triangular matrix, that is upper or lower, doesn't matter, then the determinant of A is equal to a sub 1, 1 times a sub 2, 2 times a sub 3, 3, so on and so forth, the product of the entries on the main diagonal. So if it's triangular, then you can just multiply the entries on the diagonal, and that's the determinant. Here's a proof. Suppose that A is upper triangular. Then by the cofactor expansion theorem, expanding about the first column yields the determinant of A is equal to a sub 1, 1 times capital A sub 1, 1 plus a sub 2, 1 times capital a sub 2, 1, so on and so forth. Basically, we're expanding about the first column. That's just the cofactor expansion theorem. If you're not familiar with it, go check out the previous video. Since A is assumed to be upper triangular, we must have a sub 2, 1, a sub 3, 1, a sub 4, 1, so on and so forth, all the way to a sub n, 1 equal to 0 by definition of upper triangular. Right? So, I mean, look at those entries, right? 2, 1, 3, 1. In all of those, the I is bigger than the j, right? The row is bigger than the column, so we're below the main diagonal, right? And here's what I'm talking about. That's what it looks like. We have an upper triangular matrix. All the entries below the main diagonal are 0, and if we expand about the first column here, well, I mean, the only entry that's not 0, or presumably may not be 0, right, is the first one. Okay. Hence, the determinant of A is equal to just that cofactor expansion, but that's just equal to lowercase a sub 1, 1 times capital A sub 1, 1. Why? Well, check out all those. Those consist of a sub 2, 1, a sub 3, 1, a sub 4, 1, so on and so forth to a sub n, 1. All of those entries are 0 because it's upper triangular. Okay, but that would be equal to lowercase a sub 1, 1 times negative 1 to the 1 plus 1 power times the minor sub 1, 1 of A. Why is that? Well, that's just the definition of the cofactor. If you don't know that, go review the previous video where we discuss or define cofactors. That's the definition right there. But negative 1 to the 1 plus 1 is just 1, so I could just write a sub 1, 1 times the minor sub 1, 1 of A. Easy. Just, yeah. where the minor, eb sub 1, 1 of A, is also an upper triangular matrix whose upper leftmost entry is A sub 2, 2. So the idea is that we deleted a row and a column. We're left with is still an upper triangular matrix. This is what I'm talking about. Right? That's the minor sub 1, 1 of A. It's this determinant where we've deleted the first row and the first column. Right? It's still upper triangular. We may expand about the first column of M, the minor sub 1, 1 of A, and in a similar fashion obtain M sub 1, 1 of A is equal to A sub 2 times the minor sub 1, 1 of the minor sub 1, 1 of A, right? So we can take that minor and then we'll use the cofactor expansion again, right? Except that notice that all the entries in the first column are all 0 still, right? So we do this over again, right? Where we just end up with another minor because all the other entries in that column are 0. Okay? Hence the determinant of A is equal to A sub 1, 1 times A sub 2, 2 times the minor sub 1, 1 of the minor sub 1, 1 of A by substitution. And this is what I'm substituting here, right? The original determinant is A sub 1, 1 times the minor sub 1, 1 of A. So I'm taking the minor sub 1, 1 of A, plugging it in there, and I get A sub 1, 1 times A sub 2, 2 times the minor sub 1, 1 times of the minor sub 1, 1 of A. Just substituting there. So by continuing this process, we eventually reach the minor consisting of a single entry, A sub nn. And we will have the determinant of A is equal to A sub 1, 1 times A sub 2, 2 times A sub 3, 3, blah, 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 all the way to A sub nn. That is the product of all the entries on the diagonal. QED. And that's proved. We proved it. Okay, but notice here. Hence, one way to evaluate a determinant is to perform row operations, in quotes. We haven't really discussed doing row operations yet, but they're called row operations, until the determinant is triangular. And the idea is, if you remember one of our previous theorems, that you can add a multiple of one row to another row. So you would go about eliminating entries until you had obtained a determinant that was triangular. Then you could just multiply the entries in the diagonal. At this point, the determinant may be seen to be the product of the entries along the main diagonal. Exactly. Okay. All right, so that's all for this one. Next time we'll go over an actual example of computing a determinant using cofactors and also using this little trick here of making it triangular and then just multiplying the diagonal. That's next time. See you then.